Good morning, let's get started. There's a seminar today at 1 o'clock in this room. Professor from the Health Sciences campus. Novel activators of epithelial sodium channel. 1 o'clock in this room right here. Today, getting your address. Last time I mentioned there was an error, and I figure out what it was. On the hybridization sheet, there was an error. This bond here, bond 4, is made up of overlap of what type of orbitals? Both carbons are sp3, so it's sp3 overlapping. I think in the original key it said something else. I think it said sp3. A couple of you saw that error. Okay. Those two things. We have blue sheet, we have the white handout packet. Yesterday in lab we continued on with the Newman projections, and this afternoon in lab we will also do the same thing. We'll finish up the Newman projection discussion, most of it. Okay. That means right here we're going to skip ahead to the Roman numeral 2 on the blue on the flip side, which is the voted chair conformations, and we're going to begin with that. Okay. Today in lab we'll meet downstairs, Friday group. We'll do the Newman conformation, finish that up. We'll go over the IR practice problem that I sent before the break. We'll do some IR. And then we'll begin the unknown lab, which we did not begin last week, right? So we'll have some discussion of the different techniques. You'll only be in lab half time today. Next week, Friday, you'll have pretty much the entire day. Okay? Because I want to use half of the time today for lecture. We'll talk more about lab, but right now Friday is just, you got 2 weeks to do the unknown, just like you had originally. Okay, conformations of cyclohexanes. We mentioned we're going to focus on those, 6-membered ring. We'll be looking at that. Here's a cyclohexane. Okay, we can draw these on the board, of course. We draw a cyclohexane on the board. And it looks like it might be flat on the board. Okay? Of course, every carbon is sp3. Every carbon has 2 H's. If we drew those in, if we say these two in the plane, we would say 1 forward, 1 back. We do that on every carbon, right? Tetrahedral. Still, it doesn't show the true structure of this molecule. So here we go. Here's a cyclohexane with every carbon being tetrahedral. All right. It's not flat. Here's a benzene ring. Benzene ring is flat and planar. Okay, it's very small. You see how planar it is? Boom. That would be, a benzene ring would have the 3 pi bonds and only 1 H on each carbon. Okay. That's trigonoplanar, right? And so it's planar, the plane of the board. That H is not going forward or back. And indeed, all the H's are just planar. All the carbons are planar because if you look at this, see, each carbon is trigonoplanar. So boom, 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 trigonoplanar. But because every other carbon is trigonoplanar, they're all planar. And it just makes a flat ring. But cyclohexane is not. It is not flat. Because of the tetrahedral nature. Well, just like with this, we can look at different conformations, okay, through the spinning. Now, this can't just spin because it's in a ring and you're going to just break the bonds, okay, like I just did like that. So it can't spin. But what it can do is, if you look at it, I'll hold the back still, this front can like go down, or it can go up. These are the different conformations. Now, if we turn to the side, If both ends are up, that's called a boat conformation. Sort of like an Italian gondola, with the ends up. Okay. Now the boat conformation is not the best. It's not preferred because these two hydrogens, even though they're small, they interfere with each other. They clash with each other. That's called flagpole interactions. Basically, this is the only time I'm going to show the boat. And from now on, we're going to focus on the better conformation, which is the chair, which is one end pulled down. And that's called a chair conformation, where just like a chair, you sit here, this is down where your feet can spill over, and this is the back of your chair. That's why it's called a chair. Now again, it's not going to be flat like this. Because if you did make it flat, let's try to make all the flat, with all the carbons being in the plane right through here. It was flat, okay, flat in my hand. What are the H's doing? One's right in front of the other. They're eclipsing. Okay? But if we do up and down and make it a chair conformation, now look at the H's. Can you see that? Are they eclipsing now, the neighboring H's? What are they now? Yeah, the neighboring H's are now staggered. Okay, that's one of the reasons it comes to this chair conformation. Or boat, but the boat is not as good because of those flagpole interactions. Now my model is a little bit stretched, but also in the, if I make it planar, like this, flat, what are the expected bond angles here? Well, for ninth grade geometry, that's 120. Okay? And if you make this flat, you're actually stretching out the bond angles to 120. But they don't want to be 120. What do they prefer to be? They prefer to be 109.5. And actually, in the chair conformation, the angles are more closer to 109.5. Now, we had to expect that further, but you have to just trust me. So you get better bond angles, you get your H's staggered in the chair conformation. All right, and importantly, how do you draw this on the board? Here we go. We start by drawing two lines sort of offset a little bit like this. So what are they? Parallel, but they're offset a little bit. That's actually 4 carbons right there. Okay? Now we're just going to connect these with 1 carbon. We're going to go up and connect. Good point. And over here, we're going to do the same thing, except we're going to come down. Boom, boom. Now when you do this, one time you do it, it may look good, next time it may look a little ugly. It's okay. General idea. We can erase, redraw it. Not that they do that. This one's pretty good. So what do we have here? We're trying to say, now this is supposed to be sort of 3D, where this is sort of coming a little bit closer to you, and this is kind of in the back. This end is up. And actually, this end is down. So I got my model was much larger, but this carbon is sort of up. See, I pulled it up. And then here and here are these there and there. And then over here, this one's pulled down. And so if you imagine sitting here, your back is here, and your head, sometimes you see a drawing of a person sitting here and the head, and then your feet spill over here. Y'all seeing this? I believe it's called chair conformation. Okay. But perhaps a little bit more difficult is, okay, can you now draw the H's in? Once you get it, it's not difficult, but it takes a little bit more thinking. Let's look at the H's. Here's a chair conformation. And what can we notice about the hydrogens? First off, if I take this chair conformer and set it down, you can see, especially easier to see up front, but how many of the H's, now these are all H's here, how many of them are hitting the table? Only 3. Okay? Now if I turn it over, only 3 are hitting. The 3 that are coming straight down are called axial H's. And the 3 that are going straight up are called axial H's. Those are the axial positions. Now, so that's a total of 3 up and 3 down. That's 6. What about the other 6? Because there's 12 H's on here, right? The other 6 are coming out to the side, like this guy. You see this guy here? I'm pinching. It never hits the table. If I turn it over, you see it never hits. That guy, that guy, that guy, that guy is called, anybody? What's that position? Equatorial. No matter what textbook you have, they're going to discuss these positions. They're going to call it equatorial. Hopefully you've read that, right? Okay. Axial versus equatorial positions. Let's draw these 12 H's on this cyclohexane chair conformation. Right here. Well, each carbon has an axial bond and an equatorial bond. Okay? Axial, equatorial. Axial, equatorial. Okay. Let's just draw them in. Okay. This is I call this an up carbon. These are down, that's down. Up, up, up. They're going to get straight up H's. Basically, that's straight up. That's straight up. And this is straight up. Now the down carbons get straight down. And there are your 6 axial hydrogens. Hopefully that's pretty straightforward. Now the next one takes a little bit more consideration. The other H here is equatorial, right? How do we draw it? Well, it's going to come all to the side here. It's going to be parallel, though, with the neighboring bond. Not a bond that's connected to that carbon, but a neighboring bond. So it's going to come out like this. And that are supposed to be parallel. Because if you look at it, this H here is parallel to that bond. And to this bond. Both of these and that H. Okay, so this guy is going to be parallel to not the connected bond, but the next one. And it's coming like this. This is not to the connected one, but the next one. That and that are supposed to be parallel. And that. That and that. And then this, sometimes it depends on how you drew this to make this exactly, but it's going to be, that's really not even drawn. I should have drawn it more. That's supposed to be parallel. Or actually it is good. Not with the connecting one, but the next one. This and this parallel, that's pretty good. I have them all there. So if you look at these 2 H's here, which one's axial? Hopefully, obviously, you see that this is axial. And that one is supposed to be what? Equatorial. This is the down carbon, it gets a down H. The other one is equatorial. And if we try to see here, The one that's labeled as equatorial is really this one right here. Right there. Okay. Now it's really going away from us more than I could draw. But okay, there's some 3D here where this is sort of towards you, and that's all that back there is away from you, far side. That's a pretty good looking cyclohexane chair complex. Questions up to this point? Axial versus equatorial positions. Okay, commonly to be able to show what's called a ring flip. That is, this thing can sort of, instead of rotate, it can do a ring flip where this end comes up and this end comes down. And we can go to another chair conformation. Now with cyclohexane, that one's going to be equivalent to the first one. But if we put some type of substituent on, for example, a red fluorine atom, there we go. That's a cyclohexane chair conformation. The fluorine is in what position? Axial? Yes. Now if we do a ring flip with this guy, up, down, now we got a chair conformer from doing a ring flip. Now the fluorine though is what? Yes, now the fluorine. So here the two ring flips, chair conformers, are not the same. One has the fluorine axial, one has an equatorial. And so we can say, well, of the two chairs, which one's best? And typically, you want your larger groups equatorial. There's more room there. Again, because if we look at the axial, when it's axial, now this is a small little plastic piece, but this could be maybe large. Maybe it's a large iodine and it gets a lot of electrons and it gets this big. Or maybe it's a large T-butyl group that's like real big. Well, this can actually clash with the other axial groups. Okay? Now if that's the one position, that would be 2-3. And this is called a 1-3 diaxial interactions. And that's why it's favored. And actually, they're like their eclipse. Now, they're not on the adjacent carbons. That's not good. If we turn this to make this equatorial, then there's nothing eclipsed to it, and there's just more room equatorial. Okay? So, let's first do a ring flip of just this guy. Or if we actually want to maybe put an F here, and I'll just put it in parentheses. What if that was an F? Also, let's star this hydrogen. Just maybe we want to keep track of it. And let's do a ring flip on the board. Now I'll draw it ring flipped, but once I start doing problems, I will not do this process. Okay, to do ring flip, first off, let's see if we can get that in the right position. Up, down, yes. This carbon's up and the F is axial. Okay. We're going to pull this down and we're going to pull this one up. To get like that. Now the F is equatorial. So I'm going to pull this end down and I'm going to pull this end up. How would we now draw that on the board? I drew this when I started out by drawing parallel lines like this. I'm going to do just the opposite over here. I'm going to draw them like this, offset this way. Then I'm going to connect like this. Not much of a point. And then I'm going to connect like, I'm not as used to drawing it that way, so my bonds aren't as sharp. See if I can make this a little bit more pointy. Okay, that's where this end came up, this end came down. Now, we can still put all our bonds there. That's an up carbon, up, up. These get straight up bonds. Which carbon is the F on now? If we start the carbon, which carbon is that now? I pull this end down. It's now this carbon. Okay? That's a straight up H. And this is a straight up H. Like that. These are down carbons. They get straight down, straight down. There's an F here. Is the F now axial or equatorial? It's equatorial. So down here is H. Now we can draw in the equatorial bonds. That's an F. And so now we have this end pulled up, this end pulled down. And the F is equatorial now. H is straight down there. And if this starred H over here, which one should we start over there with the same H? That H there. This end came up. Axial. When you do a ring flip, the axial becomes equatorial. Here's a very important thing. Terminology that I'll start using. The starred H is below the other H. Of the two that are connected to this carbon, it's below the other H. It's still below the other H. Here it is, it's below the other H. It's always going to be that way. But here it's axial. But here it's equatorial. Same thing with the F. The F is above the other H, or the other thing that's bonded to the carbon. Well, it still is over here. It's above the other H. Okay? We'll talk more like that as we move forward. Okay, of these two conformers here, these are two different chair conformations of one fluorocyclohexane. Which one is favored? This thing's hanging out on Saturday afternoon watching the football game. Which it's going to be more likely in which conformation? Yeah, it's this one, right? Fluorine equatorial. And so maybe we can show an equilibrium arrows, maybe something like this. Okay? You know, it can bounce back and forth, but more likely you're going to see it in the conformation on the right. Okay, how are we doing so far? Questions? A, B, C. Understanding axial versus equatorial. What about cis versus trans? Because, let's come back over here. What if we put a fluorine like this? Let's put another substituent. Let's put over here, let's put maybe a chlorine like that. Is this cis or trans?
Trans.
It's trans, right? We covered this, right? One's forward, one's back. Okay? If I had drawn them both forward, that would have been cis. Okay. Trans. That should be easy to see in the perspective drawing. Standard line bond drawing, we see the perspective of the bond. This is more of a conformation drawing. Okay, question here. If you drew a chair conformation here, would both groups be axial, or would one be axial and one be equatorial? Anybody? How are you trying to determine that? Well, nobody went for the quick and dirty and raw approach. Trans, please don't think that, hey, since you're trans, one's going to be axial, one's going to be equatorial. They're going to be opposite. Okay? It does not apply to that. Now, what I would have to do is I would have to draw this. I don't have anything memorized. Let's draw this in the best conformation. We can draw both. We can draw both of those. But would you rather have? Which would you rather have equatorial? Chlorine's large. You'd rather have an equatorial. Now it would be great if you could put both equatorial, right? Maybe we can't do that because whatever we draw has to be trans. You can't then draw a cis molecule. Let's see what we can get out of here for what type of questions we can. Okay, boom, 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 boom. Okay, I know I want the chlorine equatorial. All right, so I'm going to draw the chlorine equatorial. I like to draw in the H's that are there also just to confirm, hey, that's equatorial, the H is the axial. Chlorine equatorial, right? Why did I put the chlorine there? Why not there? It don't matter. That's why. What matters is where you then put the fluorine. Because do I want to put the fluorine here? No. That's 1, 2. The fluorine is not adjacent to the chlorine. It's, if you name this, it'd be 1, 3 anyway. Chlorine precedence because just half of them. That's 1, that's 3, right? It's a 1, 3 relationship. It better be a 1, 3 relationship here. So if the chlorine's there, the fluorine has to be where? Either here or here. Now, either may work for us now, but you get the mirror image. The way I drew it here. I have to think about it. Mirror image. Chlorine back. I think I actually want to put the fluorine here. We'll talk more about it. Fluorine here, I'll let you get away with it. I'm going to put it here. 1, 2, 3. Okay. Do I need to draw the fluorine axial or equatorial?
Axial.
Why axial? Here's the answer. Okay, and I haven't stated this yet. Here's why. These are trans. It means they're opposite. To see they're trans here, they're opposite. It has nothing to do with it being axial and equatorial. I wish I had done one where they're both equal. It has to do with how it is compared to the other bond. This chlorine is down compared to the other bond, to the H. Down compared to the H. What's the fluorine compared to the H? It's up compared to the H. One's up compared to the H, one's down compared to the H. They're trans. That's what we're supposed to draw. Okay? Now, if we can make this molecule a chair and then flatten it out. I'll keep fluorine red. And we'll make chlorine blue. Is that what I have drawn on the board? Can y'all see that at all? Chlorine is equatorial. Fluorine is axial. Okay? Hopefully I got the mirror image right. Is this the same as over here? Well, yeah. Let's look at it. First off, this looks flat. Because we know it's not strictly correct. But if we flatten this out, because we can sort of flatten it out, right? And if the fluorine is red, okay, there it is, kind of drawn like this. Flat on the board. Here's the red. What is it? Is it going away or coming towards you? Coming towards you, like the bold indicates. How about the chlorine? You see it's down here going away. See, it's the same molecule. Okay, we now have it drawn. Do we have it drawn in the best conformer? Yeah, the largest halogen is equatorial. What if we do a ring flip? What would the ring flip look like? I'm not going to draw it, but the chlorine would then be axial, and the fluorine would be equatorial. See, there's no way to get them both equatorial. You have to choose, which would you rather? And you'd rather have chlorine. Okay, what if we do, what if we keep the chlorine here, remove the fluorine over here, this guy. This guy is also trans, yeah, but it's 1,4 relationship. Okay? Draw the best conformer of this. And then tell me, in your best conformer, is each halogen axial or equatorial? Tell me the answer for each halogen. Anybody have an answer assigning the halogens equatorial or axial? Both equatorial? Yeah, I think that's right. Let's see if that's right. How can they both be equatorial? It's supposed to be trans. That's because the two don't have nothing to do with each other. They can be equatorial and still be trans. Let's see. Boop, 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 boop. I want the chlorine equatorial, so I'm going to go ahead and put it there. No matter where I start, I can start here, here, here. Once I start here, then I got to make sure that the chlorine then goes correctly relative to where I started. Right? The fluorine is 4 position, 1, 2, here. Okay, the chlorine is down compared to the H. So since it's trans, the fluorine needs to be up compared to the H. Well, this is a down carbon, so it gets a straight down bond, and then it gets the up is going to be equatorial. The fluorine is here. Yes, these are trans. Up compared to the H, down compared to the H. They're trans, and yeah, they're both equatorial. So apparently, this trans, they could both be equatorial, but here they could not be. Now please don't try to memorize every different scenario. Okay? Draw it, put it there, and yeah, okay. They can both be. Largest group. Questions? On the blue sheet, it just shows a couple of other groups and equilibriums. We'll do some of the ones that are there. But look here first. There's actually ratios that have been assigned depending on the groups. 1-methyl cyclohexane. Of course, this is the favored conformation. Looks a little naked without the H drawn there. I would always, I want you to draw the H where there's a substituent. Okay? So there's an H here, right, coming down. There's an H here, what, equatorial? Okay. Which is favored, equatorial? Well, it's 18 to 1. That's sort of been calculated based on modeling or some type of modeling. If you go to a T-butyl group, which is a much larger group, it's 4,800 to 1. That huge T-butyl group is really going to prefer that equatorial. Okay? So that just illustrates how the equatorial can be preferred, even more when the group gets larger. What's the question here? Which chair conformer of this guy, which hopefully you can come up with that name, is favored? Hopefully that's pretty easy, isn't it? Which one's favored? Oh, it's this one, the big group equatorial. Okay? Hopefully that was like the hub. Back up a little bit. Identify each as cis or trans. How about this, cis or trans? Now again, if I drew it as a perspective drawing with a dashed and bold, that would be easy. Well, this is pretty easy too once you get, okay. It's just a different type of drawing. But cis or trans is identified in this drawing structure. Which is it? Anybody? Trans. Why? Because there's an H here straight up, an H here straight down. Chlorine is below the H, and bromine is above the H. They're opposite, trans. How about over here? Yeah, that's cis. Both above the H's. How about this guy? What we got? Trans. How about this guy? Whoa. Okay, when you have more than 2 groups, cis or trans doesn't work because it becomes ambiguous. Unless you state what you're talking about. For example, here, what do you want to call this group coming off? This alkane group. Isopropyl? Is the isopropyl in fluorine cis or trans? Yeah, those are cis. What about the isopropyl in bromine? Those are trans. What about the fluorine and the bromine? Trans? All right? Fluorine is down compared to the H. Bromine is up compared to the H. Yeah. Show us a perspective drawing. That's basically like this. Yeah. Now we may get the mirror image, so let me help us not get the mirror image. I'm going to start by putting the isopropyl like this. Because if I stand up here, and this is a prelude to later on, and look down, okay, let's pretend like that's the board. And so the isopropyl is up by my head, but the isopropyl, is it going away from my head or towards my head? It's going away. That's why I drew it away there. So since it's away, what about the fluorine? Well, here we go. I've already kind of identified. These are cis, right? So if I drew that as dashed away, the fluorine is also going to be drawn as dashed away, right? They're cis. Now, here's where you get the mirror image wrong. It's 1, 2. You've got to be careful which way we are here. If I'm up here, this carbon versus that carbon. This carbon is to my left, because remember, these are like they're closer to you. So if I'm up here, it's to my left. I'm going to draw that fluorine on the left carbon, cis to that. So I'm going to put it over here, cis. This will just help us not get the mirror image. If you drew a dashed F here, I may or may not let it slide. Usually I probably will at this point, but you'll get the mirror image. Okay. Now, from there, go ahead and put the bromine. It's 1,4 to the isopropyl, so it's here. And it's trans to the isopropyl. We already identified that. So what do we do? Right here? So there's your so-called perspective drawing. Being able to go between each drawing, understanding cis or trans, etc. Anything there? Questions about that there? Type 2 questions you may see. There are other types in the workbook. Here's one. Show this in the lowest energy conformation. Question, how many groups are equatorial in the best conformation? Why don't we do that one here? Show it in the best and then tell me how many are equatorial in the best conformation. As we said yesterday in lab, and we'll say again, with halogens, as you go down, the halogen gets bigger, and that's going to be more sterically demanding. With your alkyl groups, you know, the more carbons, etc., the more branching, the bigger. It's sort of straightforward. Big T butyl group is going to be bigger than a mouthful. Mouthful is going to be bigger than a mouthful. We'll try not to start comparing apples to oranges. For example, here, obviously, the biggest group is bromine, right? Now, there's 2 of them. Like to have them both equatorial, but maybe you can't do that because of the way they're positioned and oriented. How many groups are equatorial? The answer is either 1, 2, or 3. It can be 4, if not 4 groups. Argument can be done. Why would you want that in there being the best? Anybody got the best confer and an answer to the number? Anybody? I'm liking it. Okay, so you got two equatorial. And you tell me it's one's the bromines and then the fluorine. I think I like it a lot. Let's see if that's right. Okay, I'm going to put a bromine equatorial. Have at least one. Now let's see what the next one is next door. Okay, put it here. If that's equatorial, the next one, they're cis, right? Bromines are cis, so this one's got to be what? Axial. These are cis, right? What I'm seeing is the bromines both can't be equatorial. It's equatorial. It's axial. Who's not getting that for?
Would the bromine not be above its H though? Because the way you're looking at the...
Well, there's an H here, and there's an H here.
Right.
Bromines below the H, bromines below the H. They're cis.
No, I mean like if it's coming out, like looking at just the 2D part, it looks like the bromine is coming towards you. So if you're looking at it, like I have mine bromine going axial, and that one, the bottom one's going equatorial because it's above, I thought it was above the H.
I may be doing the mirror image. Are you considering mirror image? I may end up with a mirror image here.
Okay.
We'll get the same answer with the mirror image, but that's maybe what you're looking at. Let's look at it a little bit further. Let me finish this up. Okay, I got the bromine cis. Now the fluorine is trans to those. Where do you want to put it? Well, it's either here or here. If it's there, then that's bromine, bromine, fluorine. If it's here, then it's bromine, bromine, fluorine. I'm just going to put it here. I may end up with a mirror image, and I'll tell you if it's a mirror image a little bit later. But if we put it here, and so it's going to be 1, 2, 3, 1, 2, 3. The fluorine should be what? Well, that's an up, and then that's like this. It needs to be a little bit more. I think that's enough carbon. Is the fluorine axial or equatorial? Well, it's trans to that bromine. It's trans, so the F would be here, and the H would be here. Right? So these are trans. That's right. But what do we have? Equatorial, axial, axial. Is that the best? Is that the best? What if we do a ring flip? Okay, like I said earlier, I could ring flip this from there, but I don't do that. Instead, I do the other conformation this way. If I draw another conformation, all of these are going to switch from axial to equatorial, etc. So instead of putting the bromine, this bromine equatorial, I'm going to start to put it axial. And then this bromine, which is cis, is going to be what? Equatorial. Those bromines are cis. These bromines are cis. Now if I put the fluorine here, it's trans to this bromine. So that means that it is down compared to the H. So the fluorine is like this. That's supposed to be equatorial because that's enough carbon and that the H is axial. So these are trans. So that has the same relationship as this, but that's the ring flip because everything was switched. Now I didn't pull this down and pull this up, but I can do it that way. And at this point, we say, okay, of the two, which is better? Now, one bromine is equatorial, one bromine is axial in both. So that's a wash. The difference is, would you rather have the fluorine axial or equatorial? You'd rather have it equatorial. Basically here you have two things equatorial, equatorial, and only one thing axial. So which is best? This guy. And the answer is we have two things equatorial. One of the bromines is, and then the F. Both bromines cannot be equatorial. Now once I drew that one, is that what you had drawn?
I have my fluorine up on the.
Okay, we have mirror images.
Okay.
Is yours 1, 2, 3?
I was on 1, 2, 3.
Okay, it's 1, 2, 3, and do you have the halogens? Are your bromines
Yes,
cis and your?
Yes, I have
Okay.
I have my fluorine equatorial, and then those two one.
Okay, I would let this go. In terms of it being a mirror image, let me see. They're kind of turned. I'd have to see if they're mirror images. They may be mirror images. Let me look at it before erasers. We're out of time. I'm not going to hold you accountable for mirror images because you'd really have to inspect it. Maybe you're able to get it quickly. Maybe the mirror image. That's okay at this point. During test 2, we'll learn how to distinguish between the mirror images. Okay. See some of you in lab this afternoon, yeah? Okay, guys, have a good day. All year.